Hello everyone, this is Dr. Yuzo. Today we will continue our lecture by talking about the next module, which is Module 5, Capacitor, Inductor, and their combinations. So from this module we will learn first the passive energy storing circuit elements, which are nothing but capacitor and inductor. And then we will learn the details about capacitor and inductor. And then we will learn their combinations to see how to find the total equivalent capacitance or inductance. At last, we will go through some examples to practice and assess our understandings. So, number one, the passive energy storing circuit element. So it is saying both inductor and capacitor are passive elements. By passive elements, it means they all follow the passive sign convention in IV relations. So in terms of this, there's no difference with the resistor. However, both inductor and capacitor are in nature just to store or release energy. Be careful, here is store or release rather than create. Okay, no one is able to create energy from nothing. Neither do capacitor and inductor. So in terms of this energy thing, what's the difference from the resistor then? The answer is the resistor can only consume the energy and can never store nor release. Okay? So in terms of the energy, inductor is implementing the storing or releasing through so-called magnetic field. Capacitor is implementing the same feature through so-called electric field. Since this is just a basic circuit 1 class, we won't go very deep in terms of the fields concept, but a little bit more about them. I believe a more popular term we came across before is so-called electromagnetic field. It's a very popular term used in, say, electric machine and machine drives. It is nothing but induced by electric field and the magnetic field. So electric field is surround an electric charge. A more practical explanation of this is it exists when you apply a voltage across the capacitor. Okay? Because voltage can induce the charge accumulating on two plates of the capacitor, VVC. And on the other hand, the magnetic field is surround a permanent magnet. It's a special types of material. You don't need to do anything to have magnetic field surrounding it. Or the magnetic field will surround a moving electric charge. And the more practical explanation of this is if you apply a current through inductor, there will be a moving electric charge which induce a magnetic field. So now let's learn more details about capacitor and inductor respectively. So first, the capacitor. In terms of the structure, it's made of two plates parallel placed, and there's a dielectric material in the middle, and separate two plates with distance of d. And A here is representing the area of each plate. And such structure give the capacitors. And this picture is showing the real capacitors in the real applications. And from the sides, we can tell they have different capacitance value, but as well as the voltage rating. In the circuits we studied in future, we'll have such a circuit symbol. Pretty much two parallel bars representing a capacitor, but sometimes the second parallel bar might be a curly. Okay. These are the things we actually learned from previous module 1, but here we bring up again. Okay. And then going back to the basic characteristics of the capacitor. First, the capacitance, you can imagine it is directly related to the structure we saw from this picture here. So the capacitance value is equal to epsilon times A divided by D. We just know what A and D are. And what is the epsilon? The epsilon is so-called dielectric material constant, okay, determined by the material between two plates. And second, we have charge. We have just said in previous slide that the electric field is introduced by accumulated charge on two plates. So how much charge it can have is determined by applied voltage. So Q equals to capacitance times the voltage. Next is the most important characteristic we need to know, IV characteristics. There are two ways back and forth which are equivalent to each other. The first one, if you're looking for the current through the capacitor, it equals to the capacitance times the derivative of the voltage across it with respect to time. Or the other way around, if you're looking for the voltage across it, it equals to, be careful. First, you have initial voltage V of T sub 0, and then plus 1 over capacitance times integral of the current through the capacitor. To the integral, we have lower limits, which is the initial time moment, T sub 0. The upper limit is the time moment you're looking for the voltage at. Next, the power of a capacitor is as easy as the product between voltage across and the current through. Same definition we learned before for resistor. Last, the stored energy, or say released energy, it equals to half capacitance times the voltage cross square. More about capacitor here. So the normal value of capacitance is small. What does it mean by small? The micro, nano, and pico are very euro. So you can imagine if you're seeing so-called 1 farad capacitor, you need to be aware that it is a very big capacitor. Next, in DC circuit, at a steady state, capacitor is nothing but an open circuit. What does it mean by steady state? Well, you can imagine if you apply a voltage across the capacitor, it takes time for the capacitor to hold a constant voltage across it. In other words, it takes time for charge to be accumulated. Okay? Once the voltage is stabilized, and then that is called steady state. And when it is the case, then capacitor has no current flow through, which is nothing but an open circuit. And of course, before the steady state, the time window it takes for stabilizing the voltage is called transient. Next, the voltage across capacitor cannot change instantaneously. So what does it mean by instantaneously changing? It is talking about a signal. And let's have some examples to illustrate what I mean. First, we are seeing a constant flat line. Obviously, it is not changing instantaneously, right? But on the other hand, some discrete signals like this, we can immediately recognize they are changing instantaneously, right? More examples. How about this sawtooth? Is it changing instantaneously? No, it is not. But this signal does. So it is changing from this value back down to this value at the same moment. So this is so-called changing instantaneously. Okay. More example. Sinusoidal, obviously, it is not changing instantaneously. However, how about square wave? The value here is jump up to this value at the same time moment. The same thing to the falling edge. So from this value down to this value here at the same time moment as well. So this is changing instantaneously as well. Okay. So not changing instantaneously versus changing instantaneously. So in this way we can kind of visualize the signal waveform. And also back to here again, the point is the voltage across capacitor could only look like these ways. Absolutely not possible to be like these. Now to the inductor, we also have some basic characteristics to learn. And before that, let's talk about structure as well. So we have either confined or unconfined two structures and both could induce the magnetic fields, further storing or releasing the energy. And here is a picture again we saw from previous module 1, and from the look we can tell they have different inductance value but also the current ratings. And in the circuit is simple as this. So with this structure, the inductance value, obviously again closely related to the structure, is equals to the capital N times phi divided by I. Well, we know the I is nothing but the current through it. Capital N is the number of turns of the windings here. Okay, and the phi is the flux. Next, again, very, very important IV characteristic. We also have both ways, which are equivalent to each other. So the voltage across the inductor is equal to the inductance times the derivative of the current with respect to time, or the other way around, the current through it is equal to the initial current plus 1 over inductance times integral of the voltage across it. The integral has the lower time limit is the initial time moment, while the upper time limit is the time moment you're looking for this current at. Next, the power remains as the product between the voltage across and the current through. And stored released energy is equals to the half inductance times the current square. Also in the DC circuit, when steady state, the inductor is a short circuit, meaning zero voltage across it. And the current through inductor cannot change instantaneously. Be very careful when you compare this to the capacitor, where the voltage across capacitor cannot change instantaneously. Now let's see the combinations of capacitors and inductors respectively. So to the capacitors, we obviously have either series or parallel connection. So if they are series connected, then remember the combination rule is same as the rule that the resistor connected in parallel. Okay, so if capacitors are parallel connected, then the combination rules follow the same one as the resistor connected in series. On the other hand, the inductors is kind of opposite. So when they are series connected, then the combination rule is same as the rule for resistor connected in series. And when inductors are parallel connected, the combination rule follows the same rule as resistors connected in parallel. Okay, so we have up to 4 different rules. So be very careful. And obviously here we want to review a little bit the resistors combination. So to resistors, obviously we have 2 ways to combine: series among bunch or parallel among bunch of them. So to series connected resistors, the total equivalent resistance just equals to the sum of them all. To parallel resistors, the total equivalent resistance equals to 1 over the sum of all of the reciprocal. And correspondingly, you know how to combine the capacitors and the inductor in up to 4 different ways.